Got it. All right. Let me try to get it through it here. Again, we're going to hopefully be back to that planar vector fields paper again Wednesday if I can get a few more things in order. I'm still reading and trying to understand. So back to my paper for the moment. Okay, so the determinant is a mapping from m by n matrices to A again, and it's invertible if and only if the determinant's a unit. And more than that, mx equal to 0 has non-trivial solutions if and only if the determinant is a zero divisor of A. These things are proved in the book, Matrices over a commutative ring by, I think it's Hall. So I think these results, I'm not sure where these results originally go back to, but certainly McCoy popularized or proved many of these things in around the 40s or 50s, something like that. Anyway, theorem. Let I be a subset of A. Suppose you've got these functions, at least m minus 1 times A differentiable, and you've got the Wronskian to be a unit for each z and I, then these are linearly independent. So the proof, if you set that equal to 0, we'd like to show all the coefficients are 0, right? But if we just differentiate this m minus 1 full times, we get this matrix equation, right? And so this matrix is invertible, provided that that determinant, this is just the determinant, is a unit. So the unique solution, 0. Okay. So there you go. I was, in fact, just saying these things for the last couple minutes, but there it is. But this is much deeper. We're interested in solution sets. All right, so the study of linear dependence is simplified by Abel's formula. In particular, this formula forces the Wronskian of the full solution set to remain in either the units or the zero divisors throughout the entirety of the connected subset. In the usual case, we get the result that the Wronskian's either 0 or it's non-zero for all whatever, for all time. But here we get this result. So if I have these continuous functions, some connected subset, I do need that the leading coefficient is a unit. That avoids the degenerate case. And if I have, these are solutions, n solutions of this given nth order homogeneous A-ODE, then the Wronskian is actually given by some constant times the exponential of the integral of the first to 0th coefficient of the, and so you see right there why we need that A sub naught as a unit. For Abel's formula to make sense, I need division by the leading coefficient. That's hard to do if A naught's a zero divisor. Looks like I solved your homework problem for this theorem already. Right? So I do need to actually come up with some decent problems for you guys. Suppose you got solutions to this, form this matrix of solutions. Well, this is a vector. I guess this is a row vector of functions. Then the derivative, and then the n minus 1th derivative. I mean, these are the rows in the matrix which form the Wronskian. So the formula for the Wronskian is just straight up this. It's the completely anti-symmetric symbol summed over all indices of the, here's your rows. And then apply the product rule for n-fold products on each summand, and you get this. So you differentiate the first one and don't differentiate the rest of them. Then you differentiate the second one and don't differentiate the rest of them, until finally you differentiate the last one and don't differentiate the first of them, right? And you look at it, what you got? You got a repeated row, right? Row repeat, row repeat, right? Row repeats everywhere. And so, we can break this up into a sum of these, which gives us determinants where rows are repeated in each summand. Except maybe what? Does the last one survive? Up until the last one, I think. Up until this last term, right? Well, let me think about that some more. I say all the terms vanish. Only one term remains. What's the one term that remains? That's what I'm having trouble seeing at the moment. Oh, it should just be the last one, right? Yeah, right? The last one is the one that remains, because every time, everything except for the very last term here has a repeated row already. So that it just simplifies down to this. But then what's the nth derivative? What's that? It's y1n, y2n, yn, right? And we can trade that for what? We can trade that for minus these things. So finally, on that last term in that n-fold product rule, we get to use the fact that they're solutions, right? And, well, okay, so there, I get that. But then this, right, is actually that. And when you plug that back up into there, everything vanishes again because there's repeats, except for this term. It all collapses down for the reason I pretty much just told you. Oh, here's the gory details. So, die, because there's a repeat. You know, only this thing survives. I believe. And so, and what is that though? That's exactly the Wronskian again. See, because it's the completely anti-symmetrized sum over the rows of the functions, their derivatives, out to their n minus 1th derivatives. That's the Wronskian. But we picked up this minus a1 over a naught factor when we solved for the differential equation, the nth derivative. And so we get w prime is minus a1 over a naught w. Maybe you've seen this derived in the n equals 2 case in your course, but it is in fact known for the nth order case. I actually had this in my differential equations notes, so when I got to this point in the research, I'm like, I know that one. But, hey. Anyway, and then you integrate, right? So if that's equal to that, you can basically solve dw dz equal to minus a1 over a naught w, integrate both sides, and that gives you Abel's formula. In particular, we get that w is equal to the c times the exponential of that. And then since I is connected, c is either going to be, this is a unit, right? The exponential is a unit. So either this constant out front is a unit or it's not, right? Which means either everywhere this set of functions is linearly independent, right? Or it's not. You don't, this is subtle, but when you don't have solutions, when you're just dealing with a set of n functions, and you get that the Wronskian in the usual context is 0, that does not entitle you to say that those functions are linearly dependent. There are examples of functions which are linearly independent but have identically vanishing Wronskians. It's when it's a solution set that we get Abel's formula and we get this, either or kind of behavior going on. And once you have that, then you get the theorem I've referred to already. So if we have, let's see, what's this say? I think basically it says what I just said, which is either the Wronskian's a zero divisor everywhere, or it's everywhere a unit. All right, and what that means is that we're allowed to define a fundamental solution set to an nth order problem. We have a linearly independent, I should really say linearly independent set with respect to the algebra. We could say a linearly independent to be more precise, just to make sure no one's thinking real linear independence, because that's not what I'm talking about here. Linear independence with respect to the algebra. And so that would be a fundamental solution set. And then theorem, if we have an nth order linear differential equation, continuous coefficient functions on connected I, then there exists a fundamental solution set on I. And the proof here, again, is just like the usual course, which you also did not see the proof in, because we don't do proofs in differential equations because we're not stupid. Because, well, I have on occasion, but I usually regret it. But anyway, so if we just apply the Theorem 3.3, which said we can solve any set of initial data, you pick the initial data which serves your purposes. So pick y1 such that what? Such that this is 1, 0, 0, 0, 0. You can do that. That's a set of initial data. Pick your y2 such that you have 0 for initial position, 1 for initial velocity, 0 for the rest, and so forth and so on. Just pick a set of pick a set of m functions which has the initial data which makes the Wronskian become the identity matrix, which you know gives you 1. It's a unit in any algebra. Right? And so there you go. The solution set formed by these y1 through ym will be linearly independent. So there exists a fundamental solution set, just like that. So these are the arguments that, past the initial theorem that we did based on the integral over the algebra, that's weird and new. These arguments actually are just straightforward adaptations of proofs that you guys don't, that so many students don't see in differential equations anymore because we tend to spend so much time just on applications or solution techniques, and we're kind of afraid to cover too much theory in there because, well, today's student, short attention span, not you guys. Obviously, you're still here. But anyway, yeah. What's this one? Oh, the general solution, right? If you look at any solution to this, you can form it as a linear combination of a given fundamental solution set. So there's nothing else. Once you find n linearly independent solutions, game over, you got everything. Does this sound familiar? It should sound familiar. That's the usual course, right? So that brings us to my next section, which is on first order differential equations. And here, basically, I just showcase the fact that you can still do things just like we did in Calculus 2 over in algebra. And they're actually kind of interesting what they mean. Like this one, I wanted to solve dw dz as w squared sine z, right? So separate and integrate. Separate gives me dw over w squared equals sine z dz, right? Integrate both sides would lead us to think that 1 over w is equal to cosine z. I got a minus on both sides, so I just multiplied. And then reciprocate, and that gives us this, right? Now, if I'm in the hyperbolics, then I can let z x plus jy, and my constants a plus bj, and so my w actually looks like this, because cosine z is actually cosine of x plus jy, which breaks up into cos x, cos y plus j sinh x, sinh y. Or minus, there's a minus, because it's cosine, right? Cosine of sum is cos minus sine. Daniel has proved by series arguments that these extend to arbitrary algebras, in particular the hyperbolics. And anyway, so there you go. And then I've already made the usual multiply by the conjugate trick, and it's already in. Here's your real part. Here's your j-imaginary part. These are separately solutions to the underlying real PDEs corresponding to what are the underlying real PDEs? The dw dz equals to w squared sine z. The underlying real PDEs there are ux equal to u squared plus v squared sine x cosine y plus 2uv sine x sine y cosine x, and partial v partial x equal to 2uv sine x cosine y plus u squared plus v squared times sine y cosine x. I have not done the experiment yet of posting. See, here's the fun experiment to do. You take these partial differential equations, you post them on the Stack Exchange to gauge the actual intrinsic difficulty. If your resident differential equations buffs can solve them in less than 10 minutes, But I have a suspicion that if I put these on the stack and I ask them to solve them, I'm not so sure they'll rattle this off that quickly. I don't know. I think these are kind of tough. What do you think, King?
I would give up.
You would give up? You would. Said if you're going to be on your computer, you'd be playing a game.
No, I don't.
No. Yeah, I mean, there's this u squared plus v squared thing, but it's not that. Yeah, I don't know. I mean, but I'm not an expert in solving PDEs either. So maybe there's an elite class of PDE warrior out there who just destroy that problem. This one, 3 hyperbolic numbers, right? What's the, what am I looking at here? Oh, just the exponential equation. Look, simple enough, right? d zeta d eta equal to d eta, or either the eta d zeta equal to eta. Like I get my etas and zetas separated. Anyway, so obviously that has solution. Eta equals k e to the zeta, right? But the thing is, k is a 3 hyperbolic constant, which has got 3 real variables hidden in it. And that will simultaneously solve, on the one hand, these differential equations, which are just directly d eta d zeta equal to eta, but also the H3 CR equations, namely this 3 squared minus 3, namely 6 CR equations. It's kind of neat. Let's see here. By the way, e to the j theta is cos 3 theta plus j sinh 3 1 theta plus j squared sinh 3 2 theta. These are, of course, the functions which appear in Daniel's, and Pythagorean theorem. But anyway, there's kind of neat patterns here, like cos 3 eats this j, just like the hyperbolic cos of j theta is just hyperbolic cos theta. If j squared is 1, cos, the regular cos will eat, though here j cubed is 1, so like cos 3 eats the j. Whereas the sinh spits it out, and the sinh 3 2 spits out a j squared. There's kind of neat ways that these special functions deal with the unit. I mean, the thing that makes the 3 hyperbolic special, that j. Anyway, long story short, here's what actually e to the zeta looks like in terms of its real function content. There's the real component, the j component, the j squared component. These functions, g1, g2, g3, I guess times the exponential, are solutions to this. Simultaneous solutions. That's your u, your v, your w, that satisfies this and also those. So therefore, the system of PDEs given in equation 51 finds solutions of the form this, that, or that. We got G1, G3, G2, G2, G1, G3, G3, G2, G1. And that ABC comes from multiplying that constant, that k e to the zeta out. So, I don't know, I think it's kind of interesting. At the level of algebra notation, it's just like, I knew this already. But when you study what it actually means for underlying real PDEs, it's a little bit intimidating. And I just wonder, what real PDEs are algebra equations in disguise? Because if they are, maybe I can go from equation 55, to the natural solution here, which is a world I'd rather live in if I could, as opposed to equation 55, because this is like way, way nicer for my concept. But again, I don't know if or how that's possible, that viewpoint. That's the standing problem. And then finally, just to round out this section, I mentioned that basically separation of variables, the integrating factor technique, and the method of exact equation all naturally generalize to our context. And I guess I give another, what's this example? Oh, this is just an exact equation example, I think. Yes, the other neat thing here is you can look at the differential equation over an algebra and not really specify the algebra, yet come up with solutions. And then if you think about it, those solutions have to actually promulgate, like sort of they can mean entirely different things for different choices of algebra, and yet you found this like universal solution technique. You know, that's kind of neat. Like dw dz equal to w squared. We get w equals minus 1 over z. But minus 1 over z plus a constant, rather, means so many different things for so many different algebras. As do the equations dw dz equal to w squared. Like, what do those actually play out for? It's very different. Complexes versus hyperbolic versus 3 hyperbolic versus the nilpotent algebras I hardly ever talk about. I don't know. I'm very excited about. It's shocking to me how general a viewpoint you can take, and yet how different they look when you actually get into the different choices of algebra. This must be something like the idea that algebraic geometers have when they talk about varieties, where the concept of a variety is independent of the choice of the field. Like there's a variety that means different things in different contexts. It like you kind of see this idea with like the square function. What's the square function? We all know what the square function is, but what is the square function? Like, is the square function f of x equals x squared, where x is real, different than f of z equals z squared, where z is real, or f of z bar equal to z bar squared, where z bar is something in z11? Those are all the square functions. Are they the same function, or are they different function? How do you understand that commonality? I don't know if we really give you the proper tools to understand that kind of commonality as an undergraduate mathematician. I think that's one of the things we're grappling with professionally these days. Anyway. But what do I know? Don't listen to me. I'm just some idiot who wears a crazy shirt. So, anyway. Thanks, guys.